Hello, and welcome back to the Calculus 1 playlist. In today's videos, we're going to be speaking about sequences. So we're going to define what a sequence is, talk about some properties and what they look like. Then we're going to speak about monotonic and bounded sequences, and then talk about the monotonic convergence theorem. And in the next video, we're going to go over a lot of example problems to kind of illustrate the learning from today's video. So without further ado, let's begin. So what is a sequence? So sequence. Well, a sequence is just a list of discrete consecutive numbers. So let's write that down. A list of discrete consecutive numbers. Something about sequences is that they can either be finite or infinite. And as I said, they're discrete, not continuous. So within the bounds of calculus, or at least this course, we're going to be mainly working with infinite series and sequences, which is more applicable for this course. And as well as I mentioned that it's discrete. So the values are not continuous. It's not a connected function value. And I'll show graphically what that kind of looks like. But yes, it's all the sequences is a list of discrete consecutive numbers. So graphically, or before then, let's look at some notation. What are we looking at when we say a sequence? Well, the typical notation that I'm going to use for a sequence will look similar to this. So you have an, and it's usually in curly brackets, where an is your sequence, and n is equal to the 1 is the index of the first value. So your index value n is equal to 1, and then it goes to infinity. And then you'd have something like this, where if we wanted to write out the first few terms, for example, we'd have a1 being the first term, a2, a3, go on forever. So this is this form right here is kind of the shorthand condensed form of writing what a sequence looked like, and an ordered sequence would look like. So graphically, what does a sequence look like, and how does it differ from a function? So first, let's draw out what a function would look like, and let's use the function f of x is equal to x squared, and let's just set x to be greater than or equal to 0, and you'll see why. Well, we know for x squared, when x is greater than 0, this is just a graph. Kind of just looks like that. So you have start at 0, and then you increase with the function x squared. So this is f of x. Great, so that's not too bad. We know kind of that f of x equals to x squared, what that kind of looks like when x is greater than or equal to 0. But what about the sequence of f of x squared? And we don't really use x in terms of sequence. We will use n because n is an integer number. It's not going to be just any value since it's a discrete number set. So it's f of n is equal to n squared. And the restrictions on n are n, just like x will be greater than 0 in this case. But n is also an element of the the integer number system. Yes, it's a real number, but more specifically, it's an integer. So if our n values have to be integers, what does that look like graphically? So for f of n equals to n squared, we'd have 0, and then our next value would be 1. It would not be like 0.001, or in this case, you'd have a continuous line where you could pick any number between 0 and x squared, let's say up to here, up to this point. You could pick any number or any little decimal value in between that point, and you would have a function value of that. But for a sequence, that's not the case. Your values will start at 0, and the next value would be 1, and the next value would be 4, and then 9, and then 16, and you'd go on so forth. So for f of n is equal to n squared, if we wanted to expand out the first few terms, it would kind of look like 0, 1, 4, 9, and you'll have 16, and you'll go on forever and ever. But you have discrete numbers. It's not a continuous line. Great, so that kind of makes sense. Intuitively, you could see that, and let's write out our axes properly. But something I want to talk about, and we haven't defined this yet fully for continuous numbers, but we need to define them for discrete numbers, is something called a limit. And in not the next video, but the following video after that, we're going to be starting our discussion on limits. but essentially we need to understand limits to deal with some of these problems in sequences. So a limit, we'll do it briefly without getting into too much of the mathematics. I'll do a full proof video on what a limit is in the future, but a limit is just the value that a function or sequence, in this case we really care about sequence, approaches as the argument or index approaches some value. So let's look at a point, for example, right here. Let's say that this is A, and because that is A, this is equivalent to f of A. So n is equal to A right here. I'll say n is equal to A. Well, so what do we mean when the value of the function or sequence as an argument or index approaches? So our index is n. So as n approaches this value A, so as n gets closer to A, so we're looking at as n approaches A, and that could be from both sides. As n gets closer to A, how does the function value look? Well, we would go to how the function is approaching that value. So you have the point before will be coming towards this way, and this point right here will be coming that way. So that's how the function is approaching, or other words to how it converges to f of A. So it gets closer to f of A, or it tends to, other terms, tends to approaches. Those are other words you'll hear when we're talking about limits, as we approach f of A. So that's what the limit is looking like. And in terms of notation, it kind of looks something like this. So you'll have your limit as n approaches some value, let's say A, of your sequence, f of n. Well, that is just equal to the value of f of A, because as we approach A, we're approaching the value of A, right, for that sequence, which kind of makes sense intuitively. And when we discuss limits a bit further in the videos following this one, you'll get a better sense for this. But in terms of the sequences, we just need to understand how to use limits. That makes sense. But yes, so all a limit is telling us is if a function or a sequence approaches a specific value as the argument or index approaches some value. And so to further discuss this, let's talk about some properties of sequences. So some properties. So let's say that P and N and Q of N are converging sequences. So they have limits that converge to a specific value, converging sequences. No, not all sequences will converge to some value, right? You could have some sequences that are not converging. Like, for example, a sine wave. If we look at what a sine wave is doing, it does not approach a value, right? So this is a sine wave. It goes like this forever and ever and ever. So it does not approach one value, whereas you might have some sequences that do. But we're going to assume, in this case, that our sequences are converging. Great, so say that P of n and Q and n are converging sequences. Then we have a few rules, and I'll write them down. So the first one, so let's say we have the limits as n approaches infinity. So as our index gets crazy large, as it gets bigger and bigger and bigger, if we have Pn plus or minus Qn, our sequences, well, that's just equal to the limits added up individually. So the limit of Pn plus or minus the limit of Qn of n approaches infinity. Great. So the second rule is that if we have the limit of n approaches infinity of Pn, Qn multiplied together, well, that's just equal to the limit of n approaches to infinity of the products individually. Limit times n approaches infinity of Qn. Great. So next one, let's say we have the limit of n approaches infinity of Pn over Qn. I think you could guess what's going to happen in this case. we can split up our limits as such. Oh, that's 8, it's not infinity. Sorry about that. Qn. So the fourth property, and this one also you could probably kind of get. So the limit of something of n approaches infinity, this index of c. Oops, let's make the c look better. Pn. Well, that you can kind of remove this scalar c outside of the limit p n. Great, and so for the fifth rule, and something I'd want to know about this rule, sorry about the third rule, I should also mention that it's kind of intuitive, but the limit of n approaches infinity of qn cannot equal to 0, so you don't have a discontinuous function, but it's apparent. I'll just define that for you just for clarification. So for this one, for the fifth rule, we'll have the limit as n approaches infinity of p of n raised to a. Well, we could just say that this is equivalent to the limit of n approaches infinity of pn, all of that raised to a. So you can include the limit inside. And in this case, you have to note that pn values have to be greater than 0, and the a values have to be greater than, or equal to 0. Perfect. And so the last rule that I want to talk about, and probably the most important rule in this case, would be something known as the squeeze theorem. So we'll call this VI. Squeeze theorem. So what is the squeeze theorem? What does this mean? Well, the squeeze theorem says, say we have 3 sequences, and those sequences are going to be AN, BN, and CN. And BN is bounded by AN and CN. So that kind of looks like AN here, and we'll have BN here, and we'll have CN here. Great. Then if AN and CN converge, T converge to some value L, then BN converges to L as well. So what does that kind of look like? Recall, so as we were talking about convergence or converging to f of a, so if a function is approaching a specific value at a certain index, then it converges. So in this case, as our functions get infinitely large, so let's say the limit of n approaches infinity of an, and the limit of n approaches infinity of cn, so they get infinitely large, and they both approach to some value L. They approach to the same value, then we can say then Bn must approach this value as well. So for Bn, let's write down this, the limit of n approaches infinity for Bn will also to equal to L. And what does this kind of look like? Let's show you graphically what this means. So let's say we have An, it's going to be blue. It's going to be like this. We have this function, it goes on and on and on and approaches this value here. And we have this function, let this one be Cn. And Cn kind of approaches the same value that An does over time. And this is Cn. then Bn, we'll mark it by green. Bn, recall, we said is bounded between An and Cn. So it's going to be, and I guess I should switch up the notation here. This, let's call this Cn and An. We'll switch it for consistency's sake. We'll say this is Cn, and then this is An, because we said that Bn will be bigger than An and less than Cn. Well, since Bn is bounded by An and Cn, then we can say, okay, then Bn is kind of in these, between these values. It could be oscillating or it may not be, but it's in between these values. It's stuck in between these values. Well, it turns out it will approach the exact same value as Cn and An if Cn and An converge to the same value. And that's just because it's bounded, right? As you continue to grow to infinity, it has to approach that same value. So you can see right here, and let's call this right here the value L. Well, it turns out this value L is going to be the same for all of them, since Bn is bounded by An and Cn have approached this value L. So we say then that this is the squeeze theorem, because we have our function that's being, or our sequence that is bounded by two other sequences. Great. So the next property of sequences I want to talk about are monotonic sequences. So monotonic sequences. Well, a monotonic sequence is just a sequence that is either increasing or decreasing forever. So it's pretty straightforward. Sequence that is increasing or decreasing forever. So if it's increasing forever, essentially what that looks like is An needs to be less than the next term, An plus 1, for all n greater than or equal, for n greater than or equal to 1. And if it's decreasing, you could say An will be bigger than An plus 1 for all n greater than or equal to 1. Another way to kind of write this for the increasing, I'll put it like this. You could say that An is going to be over An plus 1. Well, for this value, since An plus 1 is bigger than An, this is going to be less than 1. And for An all over An plus 1, for the decreasing case, you could say that this is going to be bigger than 1, bigger than or equal to 1. Because again, An is going to be bigger than An plus 1. So that's all the monotonic sequences. Great. And another term, a bounded sequence. We kind of touched on bounded sequences above. Bounded sequence. So let's say we suppose we have two numbers. Let's call them M and N. Then if we have the following inequality, so we have our sequence being bounded by n, so our sequence has to be bigger than n but less than or equal to m, so bigger than or equal to n and less than or equal to m, then the sequence is bounded. And again, I don't think I need to put a visual of this, but it essentially gives two number bounds on your sequences. Well, it turns out that we can use these two above properties to define the monotonic sequence theorem. And so all the monotonic sequence theorem says that if a sequence is bounded and monotonic, then it must converge. It must converge, right? So recall we said that not all sequences converge, right? Like for example, sine of x will vary from -1 to 1 forever, and you'll have other sequences that are always increasing. For example, x squared, the sequence that we talked about previously, this is not necessarily converging as you go towards infinity. It will always just be increasing, right? In this case, if you wanted to converge to a point, that's fine. But if you were talking about to infinity, f of n, when n is equal to n squared, will just keep growing and growing and growing forever till infinity. It won't be bounded. But if we have a sequence that's monotonic and bonded, it will, or bounded, sorry, it will converge. It must converge. And I'll show you what I mean, why that happens. So let's say we have a bound right here. So our sequence is bounded from the top. So let's call this y is equal to m. And we have this function that kind of goes like this. So we have an increasing function. Let's call this a of n. So we have a of n, and a of n is increasing like this. And it always has to be increasing forever. Well, if it's increasing forever, but it's bounded on top, it's just going to approach the value of this bound because it must keep increasing, but it can never touch that bound. Or it could touch that bound and never get higher. Usually speaking, we have our bound being it can never get to that bound, almost like a horizontal asymptote. It will continue to approach that point, but it will never touch that point. Then we say it is bounded and monotonic. So because it's bounded and monotonic, it is convergence. We have an increasing function that is bounded, it must converge. And it will converge to the value of m. So we would say that the limit as n approaches infinity of an is equal to m. And I want to clarify, I said that it may touch it. Usually, no, it does not. It does not touch it in any case. We won't experience any cases where it touches, but it would approach this value as it gets to infinity, right? So remember, infinity is just a construct. It's not an actual number, so we'll never get to that point. And so if we wanted to look at a case where it's bounded from the bottom, like this, say y is equal to n, then we'd have our function like this. Let's say we had a decreasing function, a decreasing bounded function. Let's call this one b of n. Well, it's going to need to decrease forever, but it's also bounded at the bottom. So it'll just approach this value forever. It needs to keep decreasing, getting closer, but never touch y is equal to n. So then we could say the limit as n approaches infinity as you go on forever of b of n is just going to equal to n. And that's basically what the monotonic sequence theorem tells us. Great, so we've talked about in today's video what a sequence actually is. We talked about notation, graphing it. Then we kind of introduced the limit of a sequence, some of those properties. The squeeze theorem, which kind of relates to the monotonic sequence theorem. But again, then we talked about monotonic sequences, bounded sequence, and a monotonic sequence theorem itself. And so in the next video, we'll go over plenty examples where we'll get practice using these sequences.